So this is the lecture 3.4 regarding the phase and phase velocity of a wave, and the course is still optics. So what I will do in this lecture is that I will speak a little bit more about the concept of phase of a wave, and more importantly, what is the phase velocity of a harmonic wave. And in this approach, I want to develop the mathematical framework that we have slightly forward, so that we would have tools to generalize our treatment of waves into more arbitrary looking waves than just harmonic waves. And in order to do that, that's where sometimes it's quite convenient to be able to describe the phase evolution of a wave and then look how this phase or phase front evolves, and then that kind of gives us, for example, how the speed of light or speed of wave changes in for example, in a dispersive medium, or when we have a short pulse and how that then changes its shape when it's propagating through a dispersive medium. So in these kind of treatments, when we have that kind of problems we want to understand, then this concept of a phase becomes more and more important. So what I will do here is that I will derive quickly the phase velocity, and I will do that using the concept of phase function. And then I will also use a total derivative to calculate the phase function, so that we will deal a little bit what the different differentials and we get to derivate things a little bit, or differentiate things a little bit. And then I will find an equation for the phase velocity, and this will be very simple for the case of a harmonic wave. But of course, when we would have more general arbitrary looking waves, then we would have more interesting time with this math. And then I will calculate what is the phase velocity of a harmonic wave. No surprises there. That will be the speed of light inside the medium. And then finally, I will describe how we could generalize this approach into arbitrary perturbations. And there we would see that in fact, when we have a more like a arbitrary perturbation, not just a harmonic wave, but something a little bit more complicated, then this perturbation may not anymore propagate at the speed of phase velocity, but rather at a so-called group velocity. So I will be ending my lecture regarding group velocity. And hopefully I can clarify a little bit about this mystique between the phase velocity and the group velocity. So this is what I will do, and I will now just get started. So phase and phase velocity. And how we will progress is that I will generalize these concepts. And in order to generalize, of course, we need to have some kind of mathematical framework that we can take use of. And our motivation is that we want to generalize the treatment of the phase of our wave, because this will help us in when and if we want to start treating anharmonic waves. Especially in the more advanced courses, when we start dealing with the propagation of ultra short pulses, then really this phase function and how it evolves becomes more and more important and useful parameter to describe things and understand things. So let's get started. We define the phase of our function, and basically what this is the argument that we have inside our sine that we already described in our previous lecture. So we have a function, and I will now describe this phase as a phi, and this equals the argument inside the sine of the wave, so kz minus omega t plus our initial phase epsilon. And this allows us to kind of figure out what is the propagation velocity of our wave. So we can look into a specific point in our wave, and we can imagine that we want to understand how this specific point then propagates. And I'm showing this soon in a figure, but this kind of propagation of a certain point of a harmonic wave then kind of gives us a quite intuitive understanding of the mathematics, what we want to do here, and why we want to deal with the differentiation of this function. So this phase phi of this exact point should remain constant. And that's the kind of like how do we define things. So we want to look at a given point which has a constant phase. And this is highlighted in here in figure, so that when we lock down into a given point of the wave, for example, this specific point, and we say, okay, this at this location at this given time, the wave has a given phase. And now I want to understand how this phase evolves, how it propagates forward. So I say that, okay, then after propagation, after some instance of time, I want to see where this exact same location where the field has the same, or a wave has the same phase, where it is now in the z-axis. And this is what I want to do. And this is quite nice, because then we can just find out where the change of our phase function is 0, and then using that we can see that this is how things progress. This is how things evolve in how the wave evolves. So the phase of the wave phi depends directly. So explicitly, that's the term on time. So this means that the kind of time dependence on the function is direct. And in addition to this, it also depends implicitly on the time coordinate t, because also the coordinate z is time dependent. And this is the kind of difference that we should understand when we now try to calculate the derivative of our function, that we must understand that some variables also implicitly depend on the variable upon which we derive things or differentiate things. So of course we should be knowledgeable of this dependence of z on time. And in our case, we are looking at the phase function, so that the phase phi depends on time in many ways. So first of all, the z, the coordinate that depends on time, I'm using this kind of notation. So z is now a function of time, and then I have an explicit time dependence on the phase function. And of course, like I already said, this changes things when we start differentiating the phase. We start calculating the total derivative of phase, and of course we should take this into account. So let's now calculate things. So let's calculate the total derivative of the phase. And why we want to calculate this is that we want to look at the phase location where the phase is constant. So if we calculate the time derivative of our phase function and then say that this should be 0, then that gives us exactly that location where it remains constant. But let's get started. So we want to calculate the total derivative with respect to time, and we apply the chain rule because we have a function of two variables, and we in addition have a implicit time dependence in our function. So we want to calculate the time derivative of phi, the phase function, and now it depends on two variables, z and t. And z in addition also depends implicitly on time. And we use the chain rule to calculate this. So first we calculate the partial derivative of the phase function with respect to z, and then we calculate the partial derivative of z with respect to time. And then plus we apply the chain rule, we also calculate the partial derivative of the phase function phi with respect to time, and then the partial derivative of time with respect to time. And this of course is equal to 0, so nothing changed strange there. And what we are left is that we are left with the partial derivative of phi over z times partial derivative of z over time plus the partial derivative of phi over time. So this is the total derivative of phi, the phase function with respect to time. And now, okay, since we are calculating the total derivative, we can really find a condition that ensures that the phase remains constant valued. And this is exactly what we want to do, because when this condition applies, then we know that the mathematics then gives us the way to understand how this point where we have a same phase propagates. So it really gives us the propagation speed using this concept of phase of the wave. So we look at the velocity of this point of the wave, and we say that the phase function must not change, and then we will look what comes out. So we calculate the total derivative, and as we already discovered, it was of this form, and then now we say that this must be 0, so that the phase must be constant valued. So now we apply the physics into our differential equation. And then we can, of course, take the equation in the middle, and then we can have the first two terms of the left-hand side, and then on the right-hand side I have the minus of partial derivative of phase function phi over time, and this is our equation. And now we can like adjust, but then we can move these terms slightly. So we can just leave the derivative of z with respect to time on the left-hand side. And since this is a partial derivative where phi has been a constant, I can slightly try to clarify the notation so that when I calculate this derivative, well, needless to say, it's a partial derivative, so in principle, like this should be constant, but this just notation clarifies that when I'm calculating this derivative, this is constant, the phase function. And now this is equal to the other cases, other terms that are left. So we have this term here still remaining in here, and we are dividing this term phi over z into the denominator of things. And I can use the same kind of notation so that instead of calculating partial derivatives, I could also just use this kind of notation that I would calculate the total derivatives while keeping z constant. So for example, this guy here, since this is a function of two variables, I could also describe this partial derivative using the concept of total derivative, but now with the parenthesis notation, I will just clarify that, hey, z is now a constant. And the same thing in here. So I have a partial derivative in here over z, and here I'm just doing the same thing using a slightly different notation. That was the point of this equality. Just to kind of show you that there's also other notations to describe what's a partial derivative. So the parameter in the sub-index, so either phi or z or t, it just shows that in this differentiation, it is a constant. So like depending on how do you what kind of terminology you use or notation you use. So the left-hand side of the equation tells us the velocity of the wave. So basically that tells us a quantity we call phase velocity, Vp. And this is what we are looking after. And now let's finally then calculate what is this phase velocity for a harmonic wave, so that we can kind of like verify that this gives us the same speed of light as earlier, and the same relation between the lambda, the wavelength, the speed of light, and the frequency. So let's finally calculate the phase velocity using this phase function. And if we have a harmonic wave, then we can simply calculate things so that we can calculate the time derivative. And the argument inside the sign of a harmonic wave is, of course, of this kz minus omega t plus epsilon. And there we calculate the partial time derivative. We get minus omega. Nothing strange here. And then we calculate the partial derivative of the phase function phi with respect to z. And here again, we get k out. Nothing strange. And now we can combine things so that we have the phase velocity, this guy here on the left-hand side, so Vp, and this is equal to the minus ratio of these partial derivatives, and we can plug in what we already discovered, so that we have omega per k propagation constant, and this is velocity, phase velocity. And we see that, okay, this really agrees with our earlier piece of mathematics, so that the phase velocity is really the velocity of a harmonic wave. And this is quite nice because now we can kind of equate these things together, so that the velocity of a single harmonic wave is known as the phase velocity. And this is where things get murky and muddy. Maybe you should ask from me or the assistants during the course, or your friend, more advanced friend, or just talk to your friends at the course, that how we can generalize this concept of phase velocity into something that is not a harmonic wave anymore. And we do not deal with this mathematics much on our course, but I will just say that this is how we would generalize, and in the upcoming courses you may need to go through this process in more details. But if you have a more arbitrary disturbance, So basically not a single harmonic wave anymore, but a bunch of many harmonic waves. So essentially we apply the superposition principle. We have a sum of many harmonic waves, and then we want to look how this kind of more arbitrary looking disturbance propagates. We see that depending on the medium inside which it propagates, is that this disturbance may actually propagate at a different velocity. And this is defined as the group velocity of light. And this is the kind of a strange thing slightly, but in this introductory course, we have chosen not to go and not to speak more of group velocity than just to say that there are these two different concepts, and we're dealing only with phase velocity in this course. But if you generalize things, if you want to understand how a short pulse propagates in a dispersive medium, so in practice, for example, if you're dealing with a problem that you have a short pulse, laser pulse inside your laboratory, and let's say that the pulse length is 10 femtoseconds, so very short, ultra short, and then you are putting these kind of laser pulses to propagate through a piece of a 1 centimeter thick piece of glass. And then your supervisor asks you to tell him or her how short the pulses are after this propagation through the piece of a glass, and then you know that it won't be any more of 10 femtoseconds. Or the person would be asking that how quickly the pulse propagates inside the piece of glass. So then you would be dealing with these kind of concepts of group velocity and what is the group index of the medium. But in our course, we do not need to go into these complications. It's just enough for us to know that there's phase velocity and there's the group velocity. Phase velocity applies for harmonic waves, and group velocity is the one that we should use when we are dealing with anharmonic waves. And most of the time, when we are dealing with only slightly dispersive materials, the group velocity is quite close to the phase velocity, but sometimes there will be deviations. And sometimes even small deviations matter quite a bit, especially, for example, in the case when you have ultra short pulses. But more on these things later in the upcoming courses. So I thank you. Thanks for stopping by, and I hope you enjoy the next lecture where we are speaking more about the superposition principle that I already mentioned, and that will be very important in the future of the progression of the course. So thanks, and bye-bye.